Hi, this is Barrett Givens, and in this video, I want to talk about these six identities about interiors, closures, complements, unions, and intersections. And I'm going to prove identities 1, 3, and 5. Okay, I'm going to prove identities 1, 3, and 5. All right, so these identities are useful sometimes when you're asked to find an interior or a closure. You can sometimes use these so that you can find it like in parts and then put them all together. All right. And they can also be useful in proofs to be able to manipulate expressions in proofs and then rewrite them in different ways. So the first two talk about how interior and closure interact with complements. So the interior of the complement of a set is the complement of the closure of the set. And then the second one says the closure of the complement of a set is the complement of the interior of the set. All right, let's just quickly think about what that means. So if I think about having a set, here's my space X, and let's say A is on the left and A complement is on the right. The interior of A complement is the largest open set that is inside of A complement. So that's the interior of A complement. And that says that we can find it by, instead of looking at A complement, look at A and find the closure of A. So the closure of A is the biggest set that contains A. So we close A and then look at the complement of that. So let's see what the proof is of this. Okay. What I'm going to do is I'm going to imagine, or I'm going to write down what it means to be in the interior of A complement using the idea of neighborhoods. So suppose, or I'm just going to say, let Y be in my space. Then Y is in the interior of A complement. And I'm going to think about the theorems we've proven about what makes that true. Okay? Y is in the interior of A complement. Well, being in the interior of A complement means for some open neighborhood U, Y is an element of U, which is a subset of A complement. That's one way of thinking about the interior of a set. Now, if U is a subset of A complement, so Y is here and U is a subset of A complement, that means that U intersect A is empty because U is entirely inside of A complement, so it doesn't touch A. U is entirely inside of A complement, so it doesn't touch A. Thus, Y is not in the closure of A. Because to be in the closure, you would say that every set U that every open set U that contains Y has to touch A. Well, this one doesn't touch A, so that tells me Y is not in the closure of A. And so that means that Y is in the closure of A complement. Okay? So what did I just show? I just showed that if Y is in the interior of A complement, then it's in the closure of A, the complement of that. And we could go the other direction sort of very similarly. So this shows that the interior of A complement is a subset of the complement of the closure of A. The other direction is similar. All right, so that's sort of the proof of one. I mean, I cheated a little at the end, but I have confidence that you can complete it. Now let's talk about the proof of three. We want to show that the interior of A union the interior of B is a subset of the interior of A union B. So one way I could do that is I could take an element that's contained in the left-hand side and show that it's contained in the right-hand side. That would absolutely work. But I'm going to be a little bit clever and do it in a slightly different way. So let's prove this. Okay, I'm going to note that A is a subset of A union B, and B is a subset of A union B. That is always true. That has nothing to do with topology. That's just a fact about sets. When you take a union of two sets, then each one of them is a subset of that union. And we have previously learned that when you have a subset relationship like this, then if you take the interior of both sides, it preserves that relationship. So I can sort of take the interior of both sides of this equation and say that means that the interior of A is a subset of the interior of A union B. I've basically just taken this equation and said, okay, now take the interior of both sides. And we know that taking interiors sort of preserves that relationship. And I can do the same thing on the other equation. The interior of B is also a subset of the interior of A union B. So I can take those two facts and like apply the interior operator to both sides. And I know from a previous theorem that it will preserve the subset relationship. So now I have two sets on the left that are both subsets of some other set. So I have some big set, which is the interior of A union B. And I have two sets inside there that are both subsets of it. Well, I can just union those two sets and it'll still be contained in the third set. So interior of A union interior of B is a subset of the interior of A union B. Okay, so that proves it. Now, you might be wondering, why didn't we say equals there? It could just be that I didn't want to prove that, right? But usually if it is true that they're equal, then, your textbook or like a video that I make or your notes, we'd probably want to prove that. So the fact that we didn't say that they're equal kind of implies like maybe they're not always equal. And so let's see a counterexample to see that, okay? Counterexample showing that the interior of A union interior of B might not equal the interior of A union B. They can be different. Sometimes they're equal. It just depends on the sets you have, but they don't have to be. So here's an example showing that they're sometimes not equal. For an example in a topology class, you first have to say what topology you're using. And you can pick any topology you want if one is not given to you. And so I would like to just use the standard topology on the reals because that is one of the easiest topologies that I have a really solid understanding of. So let's let X be the reals with the usual topology. And I'm going to let A be the set 0, 1, including the endpoints. And I'm going to let B be the set 1, 2, including both endpoints. Then the interior of A is the open interval from 0 to 1. The interior of B is the open interval from 1 to 2. Let me just fix that because I wrote it wrong. The interior of B is the open interval from 1 to 2. But the interior of A union B, when I union A and B together, I get the whole interval from 0 to 2. And so the interior of A union B is the interval from 0 to 2. And if I union up, I do have more room. Okay. If I union up interior of A and interior of B, I miss the point 1. But when I do the interior of A union B, I include the point 1. And so those are different. All right. Finally, I would like to prove 5. So 5 says the closure of A union the closure of B is equal to the closure of A union B. Let me just double check that that's what it says. Yes. Okay, so this one is equal. Okay, so for one direction, this is a set equality. We're trying to prove two sets are equal, right? We're trying to prove two sets are equal. So for one direction, for this direction, we can use a proof similar to the proof of 3 above. We can notice that A is a subset of A union B, and B is a subset of A union B. And when you take the closure operation, you preserve that subset. So we can really just completely copy this proof right here, just changing the word interior to the word closure everywhere. And it would be the same proof. And I would get that the closure of A union the closure of B is a subset of the closure of A union B. So this would give me closure of A union closure of B is a subset of the closure of A union B. And I encourage you to try to write out those details. Try to follow that proof of 3 and write out all those details, but with the closure, and check that what I'm saying here is actually true. Okay, but that'll just save me a little time here. So now we want to do the other direction. So let's let Y be an element of the closure of A union B. So one characterization we have of closure says that that means that every open set U containing Y must satisfy U intersect A union B is not empty. Okay, now we want to show that Y is in the closure of A union the closure of B. And so what I'm going to do is I'm going to use a proof by contradiction. So suppose Y is not in the closure of A union the closure of B. Well, if it's not in the union, that means it's in neither of them, right? So Y is not in the closure of A, and Y is not in the closure of B. That means there are open neighborhoods, there are open sets. I'm going to call the first one U sub A, and the second one U sub B, containing Y, for which U sub A intersect A is empty, and U sub B intersect B is empty. So let's draw a Venn diagram, okay? So I have A and B, and I'm assuming that Y is not in the closure of either of those. So Y is out here somewhere. And to show that Y is not in the closure of A means that there has to be some set U sub A, some open set that contains Y, but doesn't touch A. So that U sub A is sort of showing that Y is not in the closure. Because if Y were in the closure, a fact that is equivalent to being in the closure is that every open set has to touch A. But we know Y is not in the closure because that's what we're assuming. So because Y is not in the closure of A, that U sub A, there is some open set U sub A that contains Y but doesn't touch A. And then also there's some open set U sub B that contains Y but doesn't touch B. Okay? But U sub A might touch B and U sub B might touch A. But U sub A intersect A is empty and U sub B intersect B is empty. And now I'm going to make a whole new set. I'm going to let U be U sub A intersect U sub B. So then that means that Y is in U, and U is an intersection of two open sets, so it's an intersection of a finite number of open sets. and U is open. So U is this intersection right here. That's my U. And notice that U intersect A union B is empty. U intersect A union B is empty. That's because you can sort of see it in the Venn diagram, but U is a subset of U sub A, which is disjoint from A, and U is a subset of U sub B, which is disjoint from B. So U has to be disjoint from both A and B, and so U is disjoint from A union B. And then that would mean that Y is not in the closure of A union B. But I started this proof by saying that Y is in the closure of A union B, and then I found that it's not in the closure of A union B. And so that is a contradiction. And what did I assume to start this proof by contradiction? I assumed that Y was not in the closure of A union the closure of B. So therefore, Y must be in the closure of A union the closure of B. All right, so I've shown now, let's just recap this. I've shown that I've done a subset style proof. For one direction, I just said, well, look at the proof above and kind of copy it. And then for the other direction, I've done this proof by contradiction. I'm not 100% convinced that this proof by contradiction is the best way to prove this fact. But if I had a better way in my mind, I forgot it once I started recording the videos, and this at least works. Like, this is a true proof. There might be a more elegant proof, and I encourage you to think about that as well. At least we do have a proof. Okay, so let's go back to our statements then. We have proven statements 1, 3, and 5. The proofs of statements 2, 4, and 6 can be done in similar ways. And so that will also be left to you, the students, to do those on your own. All right, thank you for listening.